We come to today's webinar, which is called Data Management with SQL, hands-on session by Fabian. He's part also of the Vinova team, and he's also head of research data management at the German Archaeological Institute. So I'm really looking forward to knowing more about SQL, and Fabian, the floor is yours. Thanks.
Thank you very much. Yeah, thank you for your kind introduction. Today we have a webinar on data management with SQL, a hands-on session. What to expect from the coming 50 minutes that we have. I will start with a brief overview and theory, but I try to keep it very short, and I'm not going very much into detail. I'm just mentioning the things we need to know to follow on. The second part will be the main part. I really tried to do this webinar as hands-on as possible. We are going to work with a set of archaeological data. This, I have to say, mock data. I created it with a script because I wanted to have a simplified version that is really usable for this webinar. But nonetheless, it's quite representative for archaeological data. Also, you will find in real data, you will find a lot of other problems that we're not going to address today. I actually don't think we will have a lot of time left. So on the right side, you see, and also in the chat, you see what you need. This is the data encode link where you can download these slides. You can download the SQL we are going to use. I'm mainly going to copy and paste it into the SQLite browser that we are going to use due to time constraints. But there you will find everything so that you can reconstruct what we have done later on by yourself. There are a lot of resources you can access to learn SQL on SQLite and relational databases. I just put some here on this slide. That is mainly because today we really are not going so much in depth that you will be able to write SQL by yourself. Or really set up a database by yourself. The aim of this webinar is just to give you an impression what you can do and to give you an overview of some of the relevant concepts of that. But if you want to go more into detail, it's really easy to do that. There are tons of or thousands of tutorials you can find online. So let's start. What is a database? A database in its easiest form, and we really keeping it simple here, isn't just an organized collection of structured information. So you often hear things like an Excel file is not a database. That is probably debatable. In the sense of the definition, I probably would say just a table with information could also be considered a database. And for this webinar, we're just keeping to this simple definition. But we are going to distinguish between a database and a database management system. A database management system is a software that reliably stores data and makes it available for users. In practice, or for practical reasons, most of the time, if you are talking about a database, you will mean a database management system as well. But just to make it clear here, a database management system is just much more than just a file that or a single file that stores structured information. It also has a lot of components, and just you don't have to understand what's on this right side here, but just to put on one example of the different components of a database management system here on the right, you can see there's a lot going on in the background that the database management system does for you so that you can administrate and manage your data. It's going to parse your queries, it's going to optimize it, it devises a plan for execution, and it does a lot of stuff in the background also that keeps your data safe even if the power goes off or something like that. There are different kinds of databases or types of databases, or you can also say database models. There are relational databases. That's the kind of database we're talking about today. Those you probably are familiar with. It's basically a collection of tables with attributes. There are also document databases which store data in these JSON documents in that format. And just to mention some of the possible databases, there are a lot more. There are also graph databases which can store your data in a graph structure and are especially well suited for storing relationships between entities. Which kind of database you're going to choose depends a lot on your research question, of your requirements. And I'm not going to say that relational databases are the best kind of databases, but they're certainly the most or widely used ones, the oldest or some of the oldest ones. And normally, if you're talking about a database, chances are good that you're talking about relational databases. For this webinar, we are going to stick with relational databases. To give you just a quick idea of what we are talking about. When we are talking about those databases, we are talking about tables. Those tables have attributes that describe an entity. Those attributes are the columns of the table, and each entity is then described in one row and one record. So one row is one entity in a relational database. The name relation comes from its origin by Koch. It's a mathematical concept, or it comes from a mathematical concept, and we're not going into detail now. And one other thing relational databases normally have is a primary key, that is one column that identifies each row uniquely, which we will see later on. So we have relational database management systems which can contain one database or more databases, and each database has one or more tables. Why do we want to use databases for the management of our scientific data? Well, to keep data organized and findable, to ensure that data quality and consistency is guaranteed, to facilitate collaboration and versioning, for example, to separate data and analysis, so we can write code that access the data from the database, and we can cleanly separate those two things and make it therefore reusable in the sense also of the FAIR principles, and to scale storage and also our workflows, because database management systems are very good in storing and managing huge amounts of data. Now we have a little bit talked about what we are going to use, and we are switching to the part how to do that. There's a standardized query language for relational databases, SQL, which stands for Structured Query Language. And with SQL, so you can access databases and do more or less everything you want to do with it. It has a lot of advantages. It is standardized. That means it is compatible with nearly all or with all relational databases that are out there. It is quite comprehensive. That means it addresses all aspects of database management and administration. It is portable. It is not hardware or operation system dependent. It is quite performant in together with the database management system. It can process large amounts of data efficiently. It is relatively easy to learn. It's a declarative language. That means that you are telling it, or mainly declarative, that you're telling it mainly what you want it to do, and the system figures out how to do it in the background. It's much more easier to learn than a programming language, for example. And it is really widely used. That means you can easily find any resources online. If you have any problem with SQL, you just have to Google it. Or nowadays you can ask an AI system to give you an answer. There always you have to be a little bit cautious. They can tell you things that are not quite true, but with SQL, which is so widely used and not super complicated, the chances are good that you get a really good answer as well. So I said it is quite comprehensive. That means it consists of different sub-modules, let's say, or subsets of the language, which you can use to manage more or less all aspects of your data and your database. It consists of a data definition language where you can create, drop, and alter tables and columns. It consists of a data manipulation language to insert, update, delete data. It has a data query language to get information out of your database, and it has also a data control language, for example, to grant access or revoke access to the data you are storing in your database. It has much more than that what I'm showing you on this slide, but that are, let's say, the most important subsets you should know. So now we are going to talk about SQLite, which we are going to use for this webinar. SQLite is a free and open source software library that implements a relational database management system. It is self-contained. That means it has few dependencies. It runs on any operation system, and it uses no external libraries or interfaces. It is serverless, and that was especially important for this webinar. That means it can run within the application that use it is. In this case, DB browser for SQLite can easily run without any other dependencies. It is a zero configuration library. That means you don't have to install anything special for it to use it. It's just, you can just use just the files if you want, even without something like the DB browser. And it's transactional. That means that all changes within a transaction either fully succeed or have no effect, even if unexpected events such as application crashes or power failures or system shutdowns happen. So this is a quite important concept in database for database system. It's also said it's asset compliant, so it guarantees atomicity, consistency, isolation, and durability of your data. Something you can look up later if you want to. So to get back to our little image here, we are going to use SQL to manage our database, which consists of some tables that I created, or one of the tables that I created in advance to use in this webinar. One last thing I have to introduce before we can go to the handouts part is the archaeological data we are going to use. Since I assume that not all of you or just some of you have an archaeological background, I'm giving you a very, very quick introduction on archaeological data from excavations, which is by no means comprehensive, and I'm glossing over a lot of the details. But for this webinar, that should suffice. So an archaeological excavation is an invasive method to gather archaeological information about ancient material cultures. There are also non-invasive methods to gather information, like a survey where you just walk, for example, this field here in Betolonia, which is an excavation by Camilla Colombi of the German Archaeological Institute in Rome. And if you're doing just a survey, you would just gather or document archaeological material you find on the surface. And if there is a concentration of archaeological material, you can probably assume that there is something in the ground. You could also do a geophysical survey where you use geomagnetic or something else to look into the ground without opening a trench. There you can see probably the structures that you can see here in the background, the walls of buildings or something like that. But if you want to really understand what is in the ground, how it dates, what kind of find material is in the ground, and what kind of archaeological context that is, you have to excavate. An excavation consists normally of one or more trenches. A trench is what you can see here in the background, where you dig into the ground. I said it's an invasive method. That means you are going to dig into the ground, you're taking out a lot of soil, a lot of material, and everything you take out, you're not going to put back into it, so it cannot be reproduced. So if once you excavated something, you destroyed more or less the source for your data. So it's really important to document everything you excavate quite thoroughly. So we have trenches in an excavation. There can be more than one, I said. We have stratigraphic units. I'm not going into detail here as well, but a stratigraphic unit is a kind of container that tells us something about find material or about the information that we are going to dig. So it means, for example, if you are digging a hole and later refilling it with rubbish, then what you have done is you created two stratigraphic units. The one would be the hole and the other one would be the rubbish you filled in. And the idea behind that is that you can, and that's what you are seeing on this picture here on the right-hand side, you can identify those stratigraphic units because they are somehow similar to each other, and everything which is inside or related to this stratigraphic unit then belongs to one event, like digging a hole or filling it with rubbish. So stratigraphic units then have a hierarchy, or they are both another, they are cutting each other, they are below each other, and that gives us the possibility to create a relative chronology. So if something is above something else, it means somehow it is newer or more recent than the thing below. So there has been an event that is more recent than the event that created the stratigraphic unit below. That should suffice for you just to take away is that those stratigraphic units are containers, and within those stratigraphic units you will have finds, and those finds are related because they are in the same stratigraphic unit. So in our example, we have trenches, we have stratigraphic units, we will have finds, and we will have some context information, in this case, just the information about trench supervisors that have been responsible for excavating the trenches. So now it's time to go to the hands-on data exploration. The first thing, and I'm quitting now my presentation view so that you can have a look at my window of the DB browser for SQLite. It's probably a little bit hard to see everything, but you should have all materials so you can follow as well by yourself. So the first thing we are going to do now is we are going to create a new database and fill it with some initial data that I prepared beforehand. For that, we are opening the DB browser for SQLite. We are going to File and create a new database. We have to give it a name. So I'm just giving it a name. You have to choose a file extension, although that's not really so important. It does not matter really for SQLite which kind of those file extensions you're going to choose, but I'm normally sticking with SQLite 3. So that's the most general one. Then you're going to save that. You're closing this this pop-up. DB browser for SQLite gives you a lot of extra functionality. For example, it helps you create a table if you want to. You don't have to know the SQL to do that. It will create, here in the bottom part, it will create the SQL for you that then creates a table in the database. But for this webinar, to show you how it works, we are going to do everything by hand. So, or you can just copy and paste what I have written in the SQL files as well. So we're clicking on cancel here. And now we have a new database without any tables in it. What we can do now is we can import the data I prepared. Here we have to go to File, Import Table from CSV. And we are going to choose the table I have prepared. It's important that you check this first option here, column names in first line. That should be checked. It should be UTF-8. Trim fields is not so important because they are already trimmed, but you can leave that on, and everything else should be also automatically chosen for you. So field separation and code characters. You can click on OK, and it will directly show you the data in the database. So you can see we have a lot of data already in it. There are 1,000 rows, if I'm not mistaken, with a lot of different data. You can use then also the DB browser for SQLite to have a look at the database structure, like this one, where you can see that you have a lot of different fields here on this side, which have a schema that is actually the SQL that has been used to create the table for you in the background. It inferred the types of your data for you as well. That's one big advantage of databases and database management systems. You will be able to decide which kind of data type you are going to use for your attributes or your columns. That means you have a baked-in quality management feature that can help you ensuring that you don't put anything into the database which should not be put into it. There's a lot more to do that. So you can define also other constraints. You can find domains, what kind of data, what kind of values should be stored in one of those fields, not just the type of the value, but also you can decide which values you are going to store. But that is something we're not going to do today. Just one thing to mention, SQLite is a little bit loose about those types. There are just very few ones it uses in the background. It is dynamically typed. That means it infers the data type from the data that is in the column itself. It does a quite good job doing that. You can see here it already decided which values that they are in, and that's because it looked at the data which is in the tables and in the columns and inferred the types of that. But it means it's not the best language or not the best system if you really want to have those quality ensuring features. If you're using another database system like PostgreSQL or something like that, they have about 40 different or 50 different types for your data, which are very, very precise, and they're enforcing it in the database and are not dynamically typing it. They're statically typing it. That means it does not change. But for our little webinar here, that's quite sufficient what we have. We have integers, which are values from one or whole numbered values. We have real numbers, which are floats. We have text, which is basically everything which is not a number. And we have blobs for binary data, which could also be stored in an SQLite database. If you are going to change or if you're going to set them by yourself, you will also see that you could choose a numeric type, which is kind of or something which can hold an integer or a float, but it's not that's a little bit technical. It's not a storage class in SQLite, but it's something it can also infer. For you to take away as in information is just that those are dynamic type. It's more a suggestion for the database in SQLite than really something that gets enforced. So now we're going to try some actual SQLite. So let's see. At the moment, we just have this one table in our database, which is the one I created before. If you want to have a look at the data, we can do it by using the software itself. But what it does in the background is just doing an SQL query, which is, let's say, formulated for you. So you don't have to do it to get an overview of all the data. But if we want to do it by yourself and we want to learn a little bit of SQL, also the aim of this webinar is not to teach you SQL, just to show you how it works. We could write this by ourselves. And SQL normally consists of a set of keywords and then some conditions. you can add to that. In this case, we use the select keyword from the data query language of SQL. We used it in conjunction with the star, which said select, which just means select all columns. Then we normally have to say from which table we want to, or with which tables we want to do something. In this case, I just used the archaeological finds data table, which we imported. So select star from this table would just mean select everything from this table and show it to me, which is basically the same thing that browse data in this software does for you. So you can have a look at all the data here. It's all the 1,000 rows. There's no limit on what it is going to show you. We are going to, and I'm going to do this very quickly now, because it's, as I said, not the aim of this webinar to teach you SQL in depth, but just to give you some ideas. And I highly suggest that you later on take a look at the SQL code and also at some of the tutorials which go more into details. So I'm just going to copy and paste some things into here and show you. We can then, if you just would be interested in some of the columns of the data, we can name those columns by ourselves. And just one neat feature of the software we are using here, if you are starting to type something, it will suggest, for example, in this case, the columns, it should suggest tables that you could choose from, and it will help you a lot to write those queries by yourself. It will also check if something is not valid SQL. So, if we want to filter our data, we could do that with a where clause. So I could say, for example, select everything from my table where the find material is bronze, and then I will get everything from that. I could combine those conditions as well. I could say it should be bronze and it should weigh more than 500 grams. That's also no problem. It's going to do that for you. And I could use also some other keywords like the like keyword, which gives me the possibility to kind of search within text strings. And in this case, I said, give me everything which is bronze and where this find location contains a 26. And there are 2 records that actually do that. There is more I can do. I can limit my results. So if I just want to get an idea of what data is in my database, and if my database is really big, I don't want to get all the data records back, I can say limit it to 10, then I'm going to get 10 records back. I can order that if I want to. So I can order it by height. And I can decide if it's descending or ascending. I can do things like count my results. In this case, I'm just counting. I'm not getting the data back. I'm just counting how many records there are that contain finds with bronze. I have some functions within SQL to calculate, for example, an average. In this case, the average weight of the finds. I can group data by, for example, a trench number. So I'm going to group all the finds by trenches and get the average weight of the find for each trench. It's not very useful information, but just to show you that this is possible. So now I have the different trenches here, which I got back, and I have the different weight of the finds for each trench here on the right-hand side as a float. And if I want to get just distinct information, and that is something we're going to use now, then I can do that as well by using select distinct to have this distinct keyword. So I'm very quickly doing that because we're not going to really learn SQL in this really short webinar. But if you are going to use the SQL code I provided later on, you can have a look at that, and from there you can start to understand the language better with some tutorials which are specifically tailored to do that. So here on the slides is just the code I just used. So now what we are going to do mainly today is we are going to model our data. And if you have a look at our data table that we are using at the moment, you can do that by select star from archaeological finds data, and you have to put a semicolon on the last line to finish your SQL statement. Then you can see that our table is at the moment about finds. Every row you can see here is one find. And the find has a material, it has a type, it has a condition, it has a storage location, it has a weight, a height, and it also has information about the stratigraphical unit it was found in. And every stratigraphical unit has information like a soil type, a description. It has a height above. In this case, it just means it's an arbitrary height. So it's measured the relative height of the stratigraphical units. It has an extent and so on. And there's information about the trenches where the stratigraphical units are belong to. That's something I did not say before, or I forgot to say it. One stratigraphical unit normally is found in one trench, so it belongs to one trench. So you have the information about the trench, you have a start date and end date, that's information about when the trench started, and square meters, and you also have information about the trench supervisor, which when you scroll here is a list of the trench supervisor first name, last name, and email address. So it's a list within this field. It's not exactly problematic to have data in this form. When you say, okay, I'm going to document my find data, every row is a find, and I want to have all the information about one find together. But there are some problems with this kind of putting everything in a big table. One obvious thing is that you are going to repeat a lot of information, because one stratigraphical unit can have a lot of finds and one trench can have a lot of stratigraphical units. But in every row, you are going to repeat the information about a stratigraphical unit or a trench. So in this data set, we have in total 15 trenches, but we have 1,000 finds. So there are 1,000 rows which contain just information about 15 trenches, for example. We have 9 trench supervisors, but we have 1,000 rows with information. That can be a problem. If you have millions and millions of records, it can be a problem because your storage quite grows big, especially if you have 1,000 columns, for example. But it can also be a problem for your consistency, because if I'm now going to change some information about the trench, I have to do it in 100 places and not just in one. And if I'm doing that mistakenly, I have inconsistent data. That's something I want to avoid. It has advantages to have all your data in one big table, and that's all. It's actually a concept that is used in data management, to have just one big table, because it's fairly easy to query your data and it can be performant as well. It depends a little bit on your use cases, but in most cases it doesn't make sense to model your data a little bit more strict. In relational database management system, especially that is called normalization, which is a process of organizing data in a structured tables to minimize redundancy, ensure data integrity and consistency, what I talked about before. There are actually a lot of different levels you can achieve with your normalization. Today we are just looking at 3 levels, the 3 normal forms. The first one would mean that each column contains just atomic values, and each record has a primary key. At the moment, we do have a primary key, which is a find number, but we do not have atomic values. Atomic values means we should not have a list which contains first name, last name, and email address for trench supervisors. That's not atomic. So we then go on to the second normal form, which means just that the table is in first normal form and all non-key attributes are fully functional, dependent on the entire primary key. That means basically that we do have just one primary key and not a composite key of more than one key that are not dependent on each other. So just one number and not a key that is composed of many fields and where there are interdependencies. And then we're going to the third normal form, which means that you have in second normal form and you don't have any transitive dependencies. That just means that, for example, and that's the thing where we're going to really split the data, that we don't put the different entities in one table. Because now, for example, the SU information would be dependent on the SU number and not on the find number, because the SU number defines all the information, or is the key that defines all the attributes for the stratigraphical unit, SU is stratigraphical unit in this case. So we want to split those out, that we avoid having this information of the stratigraphical unit having a transitive dependency on the finds. So it's just saying we have to split the different entities in different tables. And just because I used them a lot, those terms, to give you a very, very quick overview, if I'm talking about a super key, it's one or more attributes that can uniquely define a row of a table. So for example, you can have a lot of rows, columns that together define a unique key. So like if not one value is unique, but two together are unique. First name, last name together could be, for example, something like that. If you only have people with one person that has the same first and last name, then that would be a composite key. Candidate key is then a key without any redundancies. Primary key is the key we have chosen, and a foreign key is a key in a table. We're going to see that now later on, that identifies information in another table, especially there's the primary key in the other table, and those keys relate both tables and later together, but we're going to see that very clearly now. So that's where we started from, and we are going to now separate our different entities in different tables so that we can manage them more efficiently and avoid redundancies and inconsistencies. To do that, we will separate everything about finds, everything about stratigraphical units, supervisors, and the trenches in the different tables. I'm just that you see how they relate to each other. I just put also this information in here. So one find is found in one stratigraphical unit, one stratigraphical unit is found in one trench, and one trench is supervised by one supervisor. And to do that, we can also use the SQL I provided for you. We are using the create table expression, which allows us to create one table where we have to specify a name. And now we have to specify which columns, which attributes we want to define for this table. The first thing would be an ID. We are starting with the supervisors table. Here we do not have an ID within the table itself, so we don't have a find number, a trench number, or a stratigraphical unit number that we can use as such an unique ID as a primary key. We do have a first name, a last name, and an email address in this list. You can see in the trench supervisor field from the original table, but those do not really uniquely identify one of the trench supervisors. So we're going to add one integer, which can then be used as a primary key. If we are going to do it this way, with the primary key keyword here, SQL will automatically create this key for every entry we then later on going to put into the table. So if we are going to put one name with email address, first name, last name, and email address into the table, it's going to create a number that is unique in this table and can be used as a key. So we're going to do that now. We don't see any errors here. Below you can see execution finished without any errors. And then if we are going to back to our database structure and we're going to refresh it, we can see that a table has been created for us with supervisor first name, last name, and email address. So if we go on and create also a table for the trenches that holds the data for the trenches, we do see that we have more fields than before because there are just more attributes we're going to use. We can reuse the trench number as a trench ID, so we already have one. We don't have to let it filled automatically. We can then define the other attributes. I let this one here below just in so that you can see the difference. You could put the primary key keyword here on top, or you can put it in parentheses here on the bottom. That does not make any difference. I just wanted to show you that both possibilities are there in SQLite. But we have one thing new here, and that's the relation between the trenches and the supervisors. We have a foreign key, which, as I said, references a key in another table. So we can we are modeling the supervisor foreign key. This FK stands for foreign key, so that it relates to the supervisors table and the supervisor's ID key. So every ID or every number that is stored in this attribute, which is a new attribute, will relate to the supervisor. But if you want to have the information about the supervisor, then you would have to go to the supervisor table, which I'm going to show you later. Don't worry. So, going to create that. We're going to the next table, and I'm just copy and pasting that because the syntax mainly remains the same, and it's probably best for you to understand really the syntax if you have a look on it later on by yourself. For the moment, we are just going to create those 4 tables. And if we are going back to our database structure, now we can see that we have 5 tables in total. We do have the archaeological finds table, which was the original table. We do have the finds, stratigraphic units, supervisors, and trenches tables we just created now. We can see here the schema, which is the SQL we used for it. And in this sense, you can say the schema is the blueprint for the database, which means you have all the information you need to create your database structure within this database schema. And the good thing is, for example, with the code, I could delete the table and I could recreate it very easily with the code I just provided for you. Again, I could change something, recreate it. That's really easily. And in this way, I also can share information about my database with other people. So now we have our data tables. We have 4 of them, but we don't have any data in them. So we can have a very quick look here. I'm just using the browser. Look at the finds data. You see there's nothing in finds or any of the other. Those are just empty tables that we can use now to fill it with our data. What we're going to do now is we're going to migrate our data from the original table to the new tables. And to do that, we are going to also use SQL, which provides us a good way to do that. We are going to start populating the supervisors table, and the order of doing that is somehow important because the supervisors table is the only table that does not hold any foreign key. So it does not reference by itself to another table. The trench table references the supervisors table. So when we are going to add data to the trenches, there need to be the supervisors first in the trench table. In the supervisors table, sorry, so that they can be referenced by the trenches. And that's something SQLite will check for you. So if you are going to try to insert something into the supervisors, into the trenches table, and there is no supervisors, you will get an error message. So you're doing that very basically by with the insert into keyword. Insert into, then you have to define which table you're going to insert something into, and you have to define the columns you want to insert the information into. So the next thing, the next part would be the part where you decide which information you're going to insert into it. You can just, for example, write the values by yourself if you want to enter just one record. But since we are going to extract information from our original table, we are doing a select. That means we are selecting data from the other table that should get inserted into our new table. It has to be, of course, the same amount of columns that we are going to use here. First name, last name, email. So we want to get 3 different values of it. And this following part is a little bit tricky, but I just wanted to show you that this is possible. This is a function that offers SQLite offers for us. It extracts JSON information out of an array in this case, and does it by identifying the different parts of the array. So I can just the elements. It knows JSON syntax, and it knows, okay, if there's a comma which separates the different elements, then I can find different values. And in this case, it takes an index in, so the index starts in programming languages often with 0, which means it's the first element of the array, which is the first name. The second element is the last name, and the third element is the email. And it's going to insert those as first name, last name, email into those columns. As I said, you don't have to understand that perfectly, but you can have a look on it later on. And the only other thing you have to understand is that we're also selecting different distinct trench supervisors. So we're first selecting all the distinct trench supervisors, which means the unique values, and then we are going to select the different values from those. So if we're going to do that, we're going back to our data, we can see that now we have our 9 trench supervisors, which are in the data in our database. And to not make it too long, we are going to do that for the rest as well. One by one, we are now going to put the trench data into it. And here the only thing I want to show you is that we are joining now 2 tables because we're extracting information, or we're comparing the information we have in the supervisors table to the trenches, so that we know which number to put into the trench table. We're going to do that, and I'm going to just show you very quickly that we have a trench table with data in it. It's not ordered, but that doesn't matter. It's only what we put into it. And here, this is the part where I said the foreign key gets addressed. That is the part with the join. Sorry, I have to, but go. Where is it? Yeah. The join part where we say, okay, it should be, you compare the array with what is in the supervisors table, so you can get the correct person for that. Don't worry about the details, look it up later, just so you can see it's easily done extracting information from the database structure, the first one. So we have the trenches. Now we want to populate the stratigraphical units as well, just quickly checking that they are inside the tables. So now we have 100 stratigraphical units with the information. And the last thing we are going to import is the finds table. And if we're going to do that, we should get no error and also see that we have a lot of finds in it, mainly 1,000 finds, but with less columns than we had before, because this is just the information about the finds. So the last thing I'm going to show you for today is that now you could easily do the same thing as we did before, query all the data within your database tables, and get, for example, what we did at the beginning, the average rate of all the finds for all the different trenches. And if we're going to do that, it should work quite well, but, and that's the big, or that's the thing, or the disadvantage I talked with you before. Now we would have to relate the information from different tables to each other, which makes the query we are going to use a lot more complex than the one we did before. I'm going to show you the one before also, that you can just see what we did before. I'm putting it down here. So the one before has been just 3 lines of code, while now we would have to say, give me all the finds, then look up the stratigraphical units, and then look up in which trenches are those stratigraphical units. And with that information, I can then get the average rate for each trench. So it's a lot more complex to query it, and it can, if you have tons of tables, it can get really complicated to write those queries. As I said, luckily there are a lot of there's a lot of help, and you have to decide a little bit for yourself if you are more on the side of avoiding redundancies and data quality and consistencies, or if you have it's more important for you to query the data in a easy manner. In most cases, I would advise to have strict data quality measurements in place in your database, and take the extra hassle to write more complicated queries, especially since there are so much tools that can help you there. And it's not really super complicated, it's just more code to write. But once you have understand the syntax, it's quite easily done. So, and with that, I'm going to finish, and I'm 1 minute over time.